I welcome all of you to the class. Today's class is concerned. In today's class, we'll be talking about the equation of the deflection curve, and today we will derive the equation for the deflection curve. Now, let me go directly to my chapter, my plan for today. Today we are supposed to derive the moment curvature relationship. What do we mean by the moment curvature relationship? As far as the moment curvature relationship is concerned, in the previous problem, like we had a cantilever beam and this cantilever beam was subjected to a point load, say for example P, and from the physical inspection as well, we can actually say that this beam will bend, okay, and its bending will be in this form. It will bend like this, okay. So we say that the beam is bending. Now, as far as this curve is concerned, this is actually the shape. This is the shape of the beam after being loaded. Okay, this is the shape of the beam after being loaded. Once the beam is loaded, what will be the shape of the beam? Okay, now as far as this curve is concerned, okay, if we treat this to be our x-axis, if we treat this to be our x-axis and we treat this to be our y-axis, then we can say that this is a graph, or this is a curve in an xy plane, and this curve will have some equation. Okay, this curve will have some equation. Fine, this curve will have some equation. We have to derive this equation of the curve. Number one, previously we have been relating that EI d2 nu by dx2 is equal m. Okay, this is what we have been previously using. Okay, while nu is the deflection, m is the bending moment in the beam. When we talk about the moment curvature relationship, essentially we have to derive this equation. Okay, so in the moment curvature relation, we will be essentially deriving the equation that will give us the equation of the deflection curve. Now, in order to derive the equation of the deflection curve, what we are taking a beam. We have a beam as is given on the left side, and let's suppose that this beam is subjected to a distributed load. Okay, it is subjected to a concentrated load as well as it is subjected to a bending moment m. Okay, these are all external loads. The distributed load is an external load, the concentrated load is an external load, and the moment m is an external load. Now, if we take the cross section of the beam, okay, if we take any cross section of the beam as is given here, okay, this is when you take this view of the beam. Okay, so let's suppose that the cross section of the beam is a rectangular cross section. This is a rectangular cross section. So before the application of the load, the entire cross section is rectangular. This is rectangular. The entire cross section is rectangular, and this is rectangular because no load is being applied on it. We assume the beam to be of rectangular cross section. If this beam is of the circular cross section, then it will be a circle like this. If it's a square cross section beam, then it will be a square. If it is a, say for example, an I section beam, then it will essentially be in the form of an I. Its cross section will essentially be in the form of an I section. Okay, so we are here assuming that, let's suppose that the beam is in the form of what we call as the rectangular cross section beam. Now, in this rectangular cross section beam, this is before deformation. Before deformation, the system is what we can say, this is symmetric. This is symmetric. There is no asymmetry. Okay, but once we are now loading this beam, as we apply the outside load, as we apply this concentrated load, as we apply this distributed load, or as we apply this moment m, so under the influence of this load, this beam will bend like this. Okay, this beam will assume a bend shape. Okay, so will this bend shape do? What will happen under the influence of the bend shape? That's something important that we have to see. So, as I was talking here, I was saying that this is the cross section of the beam, but let me correct it here. This is a section that is taken out here. Okay, so let's take a small section out of this beam. So I'm correcting myself. I was just saying this is the cross section of the beam. This is not the cross section of the beam. This is simply a section of the beam that has been extracted at any point of the beam. So initially, before the application of the load, we have a beam like this. Before the application of the load, we have a beam like this. But once we are applying the load, okay, once we apply the load, what will happen? It will assume this shape. That is, it will slightly be like this. Like this. Now, if we take this section out and we start treating this to be our x-axis, let's say this is our x-axis. The thickness of the small section is dx. Let's extract this dx here. Okay, so this length is dx. Okay, there's a small section. Now we take an axis from the beam. This is our x-axis. We treat this to be our y-axis. From here, we start treating this to be our x-axis. Okay, this is our y-axis. A distance measured in the upward direction will be taken as a distance measured along y-axis. This thickness, that is what we are extracting here. This is dx. Now let's from here, let's say this is also the neutral axis of the beam. Let's suppose this is the neutral axis of the beam. What do we mean by neutral axis of beam? As far as the neutral axis of beam is concerned, see, if you look at the cross section before deformation, that is perfectly symmetric. But if you look at this cross section after deformation, what will happen? The top portion of the beam, the length of the top portion will decrease. That is, the top portion will be under compression. And if you look at the bottom portion will be under tension. The bottom portion will be under tension. That is, in the bottom portion, the elongation will happen. Okay. In the top portion, the compression will happen. So it means here there is a change in length. As you move from the top portion of the beam in deformation to the bottom portion of the beam in deformation, here there is a reduction in length. Compression, that's what we are taking minus. And here is elongation in length, that's what we are taking as positive. Since this reduction in length and compression in length or elongation in length, this is perfectly a scalar. You are moving from top portion to the bottom portion. So the length sign is changing from minus to plus. Here you are having compression, here you are having tension. Okay. So it means there will be a particular length which will not change at all. That is, before deformation that was dx, after deformation that was dx. And that axis, fine, or that length which does not deform, whose length does not change after the application of the deformation, is known as neutral plane. So that's called the neutral plane. That is a neutral plane. So if we are asked what is a neutral plane, so if you look at the top plane of the beam, the top plane of the beam is in compression. If you look at the bottom portion of the beam, that is in tension. Okay. So in between there is a plane. In between there is a plane that neither undergoes tension nor undergoes compression. That plane is known as a neutral plane. And once we take the side view of the neutral plane, that will be in the form of a line. That line we call as a neutral axis. Okay. So we are treating this to be, we are assuming let this to be our neutral axis, and all the distances measured along y-axis, we are taking them from the neutral axis. Okay. So before deformation, the length here is dx, and from this neutral axis, as we are going to a distance y, there the thickness is also equal ds. We assume the thickness is ds such that dx is equal to dx, and this is before deformation. This is before the deformation, when the deformation load is yet to be applied. So the distances are to be measured from the neutral axis. So as we go upwards from the neutral axis to a distance y, the distance between the corresponding planes of the beam is or the distance between the two sides of this element is ds, such as ds is equal dx. But look, this is not the case when you are applying the deforming force. So as we are applying this deformation force, what happens? The top portion undergoes the compression, the lower portion undergoes the tension. Okay, so initially if you try to join this plane with this plane, these are parallel to each other, that is, these will be intersecting each other at infinity. Okay, they are asymptotes to one another. But once the deformation happens, the top portion undergoes the compression and the lower portion undergoes the tension. What happens now? If you produce this line, and if you produce this line, we assume that these two are intersecting at a point that is called o prime. Okay, and this is your neutral axis dx. I said that the neutral axis does not undergo any change in length after the deformation. That is, its length remains same before deformation and after deformation. Before deformation, its length was dx, and after deformation, its length will continue to be d of x. But as you go to a distance y from this neutral axis, this ds will change. It will go and become ds prime. Okay, why this ds prime will be there? Because only one length will change, that is the neutral. It's only the neutral axis that will not undergo any deformation. The neutral axis will not undergo any sort of deformation. Okay, but above the neutral axis you are having compression, below the neutral axis you are having tension, you are having elongation. Okay, so the neutral axis length will continue to be d of x, and above neutral axis the length will be ds prime. Fine. Now we say that these two axes are intersecting at O prime, fine, such that the angle between them is a small angle that's called d theta. Now the distance of this point of intersection, the distance of this point of intersection from the neutral axis, this is called rho. This is written by rho. This is called the radius of curvature. This is the radius of curvature of this thing. This is called the radius of curvature. Fine. So let's do simple analysis as has been done in this book, as uh, has been done in this book. Uh, here, here, the analysis has been done like. Okay, so what we have, the entire discussion is being explained in the form of these two pictures. Okay, so this is the before deformation picture on the left, and this is the after deformation. Okay, so we are assuming that this is our neutral axis dx, and we are measuring all the distances from the neutral axis. Initially this length was at a distance y from the neutral axis. This distance was initially before deformation ds. Now after deformation it becomes ds prime. Initially, before deformation, these two sides were parallel. Now these two sides are intersecting each other and subtending an angle of d theta. And the distance of this distance of the neutral axis from the point of this intersection O prime is known as the radius of curvature. Okay. Okay. And this point O, this is known as the center of curvature. So this is the center of curvature. Rho is the radius of curvature. Fine. Now let's talk about this ds prime. So before deformation, the length was ds of ds was the length before deformation, but after deformation it became ds prime. So how much will be the change in length? Change in length is equal, change in length of ds will be ds prime minus, we write change in length as final length minus initial length. Final length is ds prime minus initial length is ds. This is the change in length. We will write this as delta s. Now, if we divide this change in length by original length, that is ds, then this term is known as, this will be called as strain. Okay, and this strain is in fact the strain measured along x-axis. We write this sometimes as eta x. Okay, let's for some time not create a confusion here and call this as a, and start calling this as the strain. So how much is the strain produced in this ds? That is ds prime minus ds divided by ds. That is what we call as the strain. Now as far as this dx is concerned, okay, We know this is the uh, or this dx, this distance we are having here, this is rho. This angle is small d theta. Therefore, the measure of this arc, measure of length of this arc, that is dx will be equal rho times d theta. But this dx does not undergo any deformation, as our dx is equal ds. Okay, so we can write ds, dx is equal to rho d theta is equal ds. That's what is written here. Okay, fine. Now we can also write, here, as far as this dimension is concerned, this total dimension is equal rho. Okay, from here to here the length is equal y. Okay, therefore this dimension from here to here will be equal rho minus y. Okay, therefore how much will be the length of this arc, which we are writing as ds prime? Ds prime will be equal r d theta, that is rho minus y into d theta. Fine. Okay, therefore let's substitute the value of, because we had already written strain is equal ds prime minus ds divided by ds. So let's substitute the values. As far as ds prime is concerned, we're writing this as rho minus y d theta, and we have minus ds is equal, dx is equal to rho d theta divided by ds, that's equal to rho d theta. Okay, so let me clean this up. So what will be the expression like? The expression will be, this is rho d theta minus y d theta minus rho d theta divided by rho times d theta. So rho d theta and rho will cancel, so it will be minus y by rho, that's equal strain. So the strain that is produced in this, that's also written here. So we can also write strain eta by y from this equation is equal minus 1 by rho, that is this equation that is written here. So we have somehow derived this equation. Now let's talk about this equation. What does this equation, what does this equation what does this equation tell us? As far as rho is concerned, rho is the curvature. Okay, rho is the radius of curvature, and this 1 by rho, this is known as the curvature. This is the reciprocal of the radius of curvature. The reciprocal of the radius of the curvature is known as the reciprocal of the radius of curvature is known as the curvature. As far as the y is concerned, this y is the distance from the neutral axis to the plane where we are measuring the strain. Okay, and this eta represents the strain in that very plane. Okay, or strain in the element, or strain in the line element, which is at a distance y measured from the neutral axis. Fine. So as far as strain is concerned, now this is something very important. How do we define the strain? As far as, if the material behaves linearly, if it's a linear elastic material, it follows the Hooke's law, then we know stress is equal to Young's modulus times the strain. Okay, and we can therefore write stress divided by the Young's modulus is equal to the strain. Fine. Therefore, from here we can write, if we write 1 by rho is equal, in place of strain, we will now write, uh, we can write this stress divided by Young's modulus, and you have your 1. And in fact, you have a minus sign here as well. Okay, so this is a very important formula. That's sigma divided by E into y is equal to 1 by rho. Now sigma represents what? Sigma represents the stress which is produced in this plane. Okay, so sigma is the stress, or eta is the strain, E is the Young's modulus in that very plane which is at a distance y measured from the neutral axis, and rho represents the radius of curvature. Fine. We also have, in the previous semester we were talking about the stresses in the in the beams, and we already have an equation in hand, that is stress is equal minus my divided by I. Okay, stress is equal minus my divided by, this formula is known as the Flexure formula. This formula is known as the Flexure formula. Sigma is equal to minus my divided by I. That is, if we have a section of the beam, okay, such that along this section we are having bending moment M, then the normal stress along x-axis produced in this very section is equal to minus my divided by I, where M is the bending moment across the section, y is the distance from the neutral axis. As far as this I is concerned, this I is the second moment of inertia. This M is the second moment of inertia. Okay, now if we try to join the two, that is, we have this equation, 1 by rho is equal to minus 1 by y into strain, that is stress divided by Young's modulus. That's equal minus 1 by y into sigma, and sigma I just said, that is my minus my divided by I. Okay, and you have your E. Okay, so y and y will cancel. We will be having M by EI becoming equal 1 by rho. That is this equation. M is the moment, bending moment across the section. E is the Young's modulus of elasticity. I is the moment of inertia. And as far as this rho is concerned, this rho is the radius of curvature, and 1 by rho is the curvature. That is 1 by rho is equal M by EI. Okay. Now, while we are deriving 1 by rho is equal to M by EI, we are taking the help of the Flexure formula. Sigma is equal to minus My divided by I. This equation is important for us. Okay, we have done it in the previous semester. You can recall, or you can do the derivation again, how sigma is equal to minus My divided by I. Okay, now we have two equations. We have M. As far as the M is concerned, M is the bending moment across the section of the beam. We can locate it. E is given to us. I we can calculate, but this rho is something different for us. As far as rho is concerned, calculation of rho is very, very difficult in terms of beams. Okay, so how do we calculate this rho? So we are saying 1 by rho is equal to M by EI. We need to revisit this equation. This equation needs to be revisited. Why do we need to revisit this equation? Because this calculation of rho is very difficult for us. We want to reduce this equation into a form where our dependence on finding this rho is, is nullified. We want to make use of this. We want to reduce this M by EI is equal to something. We want to represent this rho in such a form that we need not to find the rho directly, because finding rho in case of beams is very, very difficult, and in fact it's impossible to find rho. So what we will do in the next class will be, I think, going to this slope and displacement. We will be reducing this 1 by rho into a form which helps us in writing it in a more compact form, that we shall be hopefully doing